dear participants, as usually, I would like to ask you to close to your microphone and camera, but of course you can ask Professor Peng your questions during his talk. So
okay, yes.
Professor
Yes.
Peng, you can start, please.
Oh,
You
thank
have
you.
1 hour, 60 minutes.
So it's my great pleasure to have an opportunity to give a lecture in this the very famous center of probability from earlier Komorov and now is Professor Shige and all the leader here. Is thank you very much. The title is Theorem Method and the Contents of BSDE and the Nonlinear Expectation Theory. I'm sorry. We recall that in the foundation of probability of the Kolmogorov given a triple of the triple of probability, triplet, so maybe triplet, I'm sorry. And here, in many cases, we need to calculate the expectation of random variable, just like it's thanks to the integral or integration of Lebesgue type. Then we can follow Professor Kolmogorov to this very basic but here challenging problem of finding the true probability P set from the set of probability is challenging problem, and solving this uncertainty. So this is the uncertainty of finding this P set has a lot of problem, and especially also recently the problem of deep learning also related, okay, or also directly related, and in this case, to consider to this sublinear expectation, the notion of sublinear expectation to this is quite simple. Is you just use the maximum of expected value of x, the maximum of, and then this E become a sublinear. The sublinear with respect to to random variable x. And then we can here give omega have a triplet by using the E, sublinear E. Okay. And usually the sublinearity, the stronger the sublinearity and the larger the uncertainty of this P set. Okay. We have the book we have is give a system discussion about this and emphasize the sub linearity. Let us think about the case of classical Brownian motion. Sorry, it's the case of classical Brownian motion, and in this we just consider the space of d-dimensional continuous paths starting from 0. That is the whole omega is the path, the collection of paths of this C0. Okay, and the corresponding canonical process is given, is classical given, and then we have the all paths to be the set omega, and let H be a dense linear space of path functions of omega. That is part. It's in this example, it's just a path. H is a random variable. Okay, it means that it's a function of path, and we can just give the H for all possible phi. For each possible phi, phi of the BT1 minus BT2, BT2 minus BT0, sorry, BT2 minus BT1, till BTN minus BTN minus 1. Here, if we take all such kind of form, it constitute the random variables, our random variables, and it's especially we can arrange such that the T0 strictly smaller than T1 till Tn. Okay, we then define the Wiener expectation E on the space. This is defined on the space of random variables that mentioned this H. Okay, then we what remain for this triplet, what remain is just is only the E. Okay, it's important. It's E. How we define such E in such that the the B, the canonical process B become Brownian motion. How to do? But it's also quite simple, since we according the definition of Brownian motion, the increment of all stable, independent, and they are all Gaussian or normal. Okay, normal. It's the normal. This random variable is identically distributed, like T1 minus T, the square root of T minus T2 T0, say 1 till Tn square root of Tn minus 1, say where psi I is IID random variable with the coherence ID. X. Yeah, okay. In this case, of course, the value of expectation x EX is explicitly given, and so it's just we just need the calculation like this, and the FT conditional expectation of x is even easier. Because we just instead of calculate all this the expectation is TK is just need to firstly take take fix or frozen x1 to xk, and calculate this random variable, the expectation of this random variable, and then the conditional expectation is just using we already calculate once by fix x, and we get function, and then we calculate again. Okay, then we need no more calculation. We just need to put x1 to be bt1 minus bt0 till to put x to x k to be btk minus btk minus 1. Okay. So in this way, the expectation is already the of E is also decided. Okay, it's determined. So in this way, we have already have obtained the value of expectation on the space of random variable H. And also this E just satisfies positivity and the keeping constant and the linearity. Okay, and also it's easy to prove that when sequence xi in H converges to 0, this means that the expectation of xi, the value of expectation of xi converges also to 0. Then we can use the well-known Daniel-Stone theorem so we can use the theorem, the Daniel-Stone. But the important thing is that we already had this has a norm. The important norm of L1 is just defined, and then after with this norm, the pre-Banach space, in fact is a Hilbert space. The pre-Banach space becomes L1 in this complication, the completion of H, this random variable space, and then this gives us the omega also this also after this we can also come back to omega ftp. Okay, and also we can extend the expectation operator to the whole space of L1, and the related EDOS stochastic analysis and the martingale theory can be followed, also can be followed in this line. Now we think about the case where the expectation is sublinear. In this case, we still assume that this as we just talk about an example, but in general, a nonlinear expectation is just the functional E defined on H, the random variables, satisfying the monotonicity and keeping constant and the sublinearity. Okay, and in many cases we also ask if this for each sequence of xi downwardly, monotonically downward to 0, satisfy this condition or not. If it is satisfied, then we can use the nonlinear, the so-called nonlinear Daniel-Stone theorem to prove that there exists a family of probability measure P set, the whole the set defined on this omega and sigma algebra of H such that EX becomes EX is nothing but the maximality of the integral with respect to p theta. Okay, so in this way we can go this way to come back to come to, and then after this after this after obtaining this omega h e for Brownian motion, just for, sorry, I cannot see clearly. It's this E, then the definition of omega h is it can be exactly the same. What is different is for this triplet. This we define omega h as a random variable, and the expectation of E of h, which defined to be like this, or to be like this, where of course we use a new E, which is thing, but the expectation of E h1 to hn, which is this, but this can be devoted. The difficulty can be solved just because this, in fact, the expectation of this is nothing but just E of x in square root of t minus t1 t0 times x1 till t minus t of n minus t of n minus 1 x1. And we just because of the Brownian motion, the so-called Chi Brownian motion is that it is satisfy satisfy the assumption that the increment is independent from what is the path before t and before t minus 1. Okay, the path before and also it's also needed that here this is and is independent. Is because here the dependence have direction. We know that btn minus btn minus 1 is independent from all the other. And also, for example, BT2 minus BT1 also independent from BT1 minus BTN, BT0. So it's BT0. So we have from here we can prove that this omega HE become a sublinear expectation. Okay, become a sublinear expectation, and here we mention about the two important notions. The one is the so-called identification or identical distribution. Identical distribution. X is X is the same distribution like Y if and only if for each phi, for example, bounded continuous function phi, the test function phi, they are the same. Okay, this is the independence. The independence is the so-called Y is independent of X, means that the calculation of phi of XY is not is just the case where phi we first fix X and calculate the expectation of phi of XY. Okay, of phi of XY, and then calculate the X, put this X to be random variable X, and take the expectation again. Here, of course, the expectation is just sublinear. In fact, it's not just even in more general nonlinear. It's we can still use this the same argument, the argument here to define more general situation. But we also emphasize that in this setting, Y is independent from X does not imply X is independent from Y. In fact, we can see clearly that in this formulation, even after the is X pairs realized before Y. So before Y, it's like two random variable, one random variable today. X realization is X. Tomorrow is the realization of Y. Okay, so as the independence means that even with the realization of X, I don't change the distribution of Y. But this distribution is means that the distribution means a subset of a distribution. Okay, we see also in this setting that in fact BT, the increment of B of Brownian motion, the T Brownian motion B is Gaussian. Okay, is Gaussian, and this Gaussian also satisfy this relation, square root of s, because say 1 plus square root of t, say 2 is identically distributed like square root of s plus t times say 1. Okay, times 1. And this gives us the distribution, the normal distribution, the normal centered normal distribution. We just need this, define this, and this normal distribution, centered normal distribution, is completely determined if we have this G. Okay, if we have this G is and the G is a deterministic function, which is sublinear in A, and still monotone. Okay, still monotone in A, monotone in A. That's G of B1 is bigger than G of B2. No, V1, G of A1 is bigger than G of A2 if A1 is bigger than A2. Like A is symmetric matrices. Okay, so we have and after this, we after completion, just like before we have a completion, we go to this completion, the corresponding expectation, sublinear expectation is called the EG. It depends on G, you see, and also LP. Okay, LGP is we can, and in this space we still can have a generalization of Edo's formula, but here the Edo's process becomes to be the starting point, which can be constant, and the ds part, the db part, and the square root of b part. So we here is that this cannot be deduced to be ds if it's it cannot be so more precisely, if xt identically equal to 0, if and only if x0 is 0, alpha t is identically equal to 0, beta t identically equal to 0, gamma t also equal identically equal to 0. So this provides a very powerful relation, the tool for us to see to see in more detail about the risk hidden behind this this type of ethos. So this from this we developed also some kind of martingale and other things which depends. It's very similar, like here. Here is also we also can work with backward stochastic differential equation driving by Brownian motion. Okay, G Brownian motion by driving by G Brownian motion. And also another interesting thing is that we can see here xt xt to be the function of path. Okay, of course we at the beginning we also already from it's the function of path is already a function of path, and here we can see this alpha s to be the derivative of function of path with respect to t. Okay. And this can be see like the derivatives of this function of path with respect to x. Okay. With respect to x. And this one, gamma s, because it's quite interesting that this they are written. So we can, in some sense, arbitrarily take all such of random process. Of course, it's adapted. Okay, adaptive. Adapted process, but we can see here gamma s is second order derivative of the random path. Okay, so it's that what I mean is that makes the things quite different. Of course, it's a generalization. Once, for example, G, once this G become linear, this function G becomes linear, then this term is and this term becomes the all ds process of ds. Okay. So another question is why we need the nonlinear. Why we need the nonlinear. Is we just see an example to I'm sorry. Okay. Here we we see here example of as in machine learning, in machine learning. In machine learning, in many cases, especially in supervised machine learning, we just give a sample, okay, sample, and this sample is usually see as independent and identically distributed data. This data can be written like xi, yi. Yi is something to be used to supervise the machine, to like this, we need to under this x1 minus x2, the expectation is need to be the smallest one, okay, so smallest one, and in here we use people use the Monte Carlo method, because in this case we see that the average of fxi minus yi square is when m sufficiently large, it becomes very approximate to the value of this expectation. Okay, just because it's ID, we know that this but of course no one believe this is true. Okay, this is true. In fact, we take many sample and ask if they are identical, independent. Okay, many standard sample, but the answer is no. It's still far from IID, But here we can see that is not is IID in a nonlinear expectation with respect to nonlinear expectation. Of course, it's here we mentioned Monte Carlo method depends on the well-known classical law of large numbers. Okay, large number. Also, we have the so-called central limit theory, telling us that the xi is independent and identically distributed random sequence, such that the sequence where is they satisfy this condition. Then we know that this sum, when n is large enough, it converges in law to the normal, the normal distribution with sigma square. But of course, if our data is not an ID, and it becomes very difficult because we can also is just like many possibilities. Like at the very beginning, I write the p theta. Okay, it's just many infinite possibility of so it's our opinion is to see this in the case of course this is just our calculation how to classically how to get the expectation under IID assumption. It's a very classical and very widely used, but is classically is but we now we consider case where we have probability uncertainty, and of course in this case we can define the expectation, sublinear expectation. The sublinear expectation, the advantage of sublinear expectation is that if you have see about this, if you have two line straight line, the two red color straight line, they cannot compare each other. I mean, you cannot say line 1 is bigger than 2, or line 2 is bigger than 1. Just because any line is all they are identically equality. So, but the sublinear has its advantage. So you can say that one sublinear line is bigger than all the other one. Okay, or the other one. You can just we can just profit this, and so there are possibility to have many lines behind this blue line, behind this blue line. This gives us so that's why the sublinear expectation can be dominate any given sublinear expectation. Okay, and we can use one sublinear expectation, sublinear expectation operation to dominate all other one. Okay, or any given one, or any given subset of expectations. Okay, so it's just because this we have now. Then when we define the the corresponding then we have f5. We have f5. f5 is a sublinear. Okay, it's sublinear. It's just the expectation is of course here is simply called distribution. The sublinear distribution is simply sorry. It's then the uncertainty of distributions of random variable x can be also, of course, defined like this, which is gives us even for any given x random variable or random vector x, then we can have we can have to have this a strong sublinear expectation such that for each random variable x, this is bigger than all about this. Okay, this is what we call the universality covering. The universality covering means that we can find the one sublinear expectation and to use this to have to dominate many other one, and in is this is usually we use this universal covering. We use this universal covering to study the case of for the sake of this I'm sorry, it's okay. I think I'm so, some example of ID. The example ID is just consider we have a black box. We have inside the black box. We can it's just the generator of random number generator. In which we don't know it's the probability distribution of this random variable. We don't know. We just know it, for example, it's contains in a subset of distributions. We just know each time we draw one. Oh, sorry. Oh. Okay. I'm sorry. How long time it remains?
You have 5 minutes, but we can give you, for example, additional 10 minutes. So you have maybe 15 minutes, if okay for you.
Thank you. Thank you.
Mhm.
Okay. Okay. So we this what I mean is we don't each the generation of ordinary ID is the generator of ordinary ID random variables is just each time they give a data a sample randomly, but we know the distribution. Here we don't know distribution. We know only a set of distribution. Each time, and it can change from this f theta 1 to another theta f2. So in this case, we have the nonlinear ID. Okay, we have the nonlinear ID, and in this case, we can check that in fact this corresponds to the situation where psi I plus 1 is independent from xi 1 to xi, but we cannot say that xi 1 is independent from xi. Okay, we can say that this is only one way independent, but it's in fact in this of course covered the classical ID as a special situation, and it gives us more, far more. So it's so we have also the universality of ID. If we that means if we are in the sublinear expectation, the ID assumption can be very near, very near, and this explains the robustity. Okay, robustic robusticity. Okay. Then we so the question now is if we can this in sublinear situation, this becomes the convergence becomes more more realistic. Okay, more realistic. But can we get the distribute the distribution we have, the distribution, the limited distribution we have is first, we call this if x plus the x bar, where x bar is independent copy of x, then x plus x bar is is identically distributed like 2x. This is what we call the maximal distribution. And this one, y, it's also x, y plus y bar. If it's identically distributed like a square root of 2y, then we call it them central the normal distribution, normally distributed. And I try to explain why the first case, the average of the first case converges to maximal distribution, and the second one converges to the normal distribution. So okay. Do you have question?
No. It's a little
Okay.
problem with connection.
Okay.
So, okay,
Okay.
please
Right.
continue.
Okay, thank you. Here we have we can see like this. Assume that they are convergent. Okay, for example, y. They converges this converges when n to weakly to y. Then we can see that when n is large enough, and then when we take y1 we put them 2, then to split, okay, the two. So it in this case, you see the square root of n, and this is the square root of, and they are, of course, very, very near y plus y bar, okay? It's but it's just the intuitive explanation. To get, of course, we can use this intuitive to construct a method to prove the limit behavior of law of large number and the central limit theory. And the convergence is just what I mean. This is maximally distributed. Maximally distributed, so becomes you see this. We can for this we can define a function u for any given phi. This phi is given, for example, Lipschitz or abundant. So continuous function, but we can define utx given this, and this utx is just we can prove it if they satisfy this this distribution. Then it's just the solution of this PD as a PD. I call it the small g PD, the small g. This and we can also have v of tx, which is given like this. The only different from here is this is 1 minus t, this is 1 square root of 1 minus t. And then we can prove that they become this one. Okay, this is important because it's linked directly to the case where if we can calculate the distribution of because if we test use all phi, then we get the what we need. This is the distributions meaning. The meaning for its distribution is here, and this on the other hand, once we can we can have this. Once we can have this, and then we just need to put x equal to 0, t equal to 1. Then this is t equal to 1, x equal to 0. Then t equal to 0, x equal to 1. Then it's just e of phi of x. Okay, so this is what we mean. We need. So we solve this PDE. Then we have this. Okay, then we have the value of e phi of x. Of course, so this is so we can use this part, which is the sort of generalized Monte Carlo. We can come here also, which is PDE. Okay, we can use who part, but the problem, one problem is why we have no such kind of phenomenon in classical case, because this is the generalization of classical case. I just think the answer is that in classical case, G, small g, and big G are all linear, okay, and we can solve when it's linear. We can solve it, and this small g is just that. We will see later. We just and this one, for example, this one, we can prove that is because when G is linear, it's Haight equation. Haight equation have a kernel of normal distribution. Okay, so it's just say that this is normally the convergence is to normal distribution. Okay, and also this one means that when G equal to 0, no more. Okay, I'm sorry. So we have this. We have also compare the parameter. For this give us a distribution. This distribution have a parameter. The parameter here is mu lower bar and mu over bar. And for the Shige equation, we also have this, but which is sigma upper bar and the sigma lower bar. Okay, and which is that gives us two parameters to fix this distribution. Okay, this is law of large number, which see that tells us that the classical case is just the case where mu lower bar is equal mu lower bar. Okay, mu over bar equal mu over bar. Okay, it's equal, so it's constant. It's just the expectation of E of x1. Okay, expectation of x1. And then we can use this to the data analysis. We used this, and it's quite I think quite powerful to okay and this is the case we are do the estimate the estimation how to get this sublinear expectation. Just the sublinear what I mean is you see if we have if we want to calculate calculate by using sample if we want to for a given any given phi if we want to calculate this value estimate this value. If we want to estimate this value, then we have already this. They are IID. Okay, you take phi is still IID. They are IID. Okay, and we divided this in M group. Each one is IID, okay, and each one is IID. But according the law of that number, it's this will becomes the sublinear expectation of x, of phi of x, okay. Then we can have we can use the I think the very basic the number we can use this to be the ID because it's called us that if x1 xm is ID and also maximally distributed, then we can estimate this mu of n to be, you take the group 1, you take the group n, and you can take a maximum. The case of a maximum comes from the maximal distribution. That's means it can be used in many situations in the sorry. Okay. Also, we can get the convergence. Okay, the convergence rate of this IID sum. Okay, I think that's all. I'm already very late. I'm sorry.
Yeah.
Thank you very much.
Thank you very much, Professor Peng, for your talk and for new results. As I understand that some of the last results not included in your book about nonlinear expectation. Thank you so much. And maybe some colleagues have questions, short questions or comments, please. Dear colleagues, please. Oh, Professor.
Okay.
Yeah. Oh, Professor Ulyanov, please.
So thank you very much, Professor Peng, for very interesting and deep talk. In fact, research concerning nonlinear expectation continues already more than 25 years. And it's surely not enough time to cover all results, all very interesting and deep results in this direction. But I would like to draw attention to my recent review paper about nonlinear central limit theorem. You can find it in chat. I send it in chat.
In chat?
In chat.
Mm-hmm.
In chat. So, okay, thank you very much again.
Thank you.
Thank you once more, and with great pleasure, we will invite you to take part in our next seminars. And now I would like to announce our next talk. The next talk is a talk of Professor Yaroslav Sergeyev from Calabria University, Italy, and Lobachevsky University. And his talk, the title of his talk, Computations with Numerical Infinites and Infinitesimals, and Infinitesimal Probabilities. And I repeat it for our Russian participant. Доклад называется «Вычисление с бесконечно большими, бесконечно малыми величинами и бесконечно малыми вероятностями». Встречаемся с вами в следующую среду. We are glad to meet all our participants the next Wednesday in our usual time. Thank you very much, and we finish our program for today. Professor Peng, thank you once more.